Record. Okay, from now on it's recording, okay? Are you taking notes or not? I usually, scan these and post, but since I'm not at school, I've not been doing it, but I'll try to do it. Okay. TG, are you okay?
Yes, ma'am.
Okay, thank you for reminding me.
Mm-hmm.
Okay. So that's the acetyl with OET. Now look at the equilibrium here. That's what they're talking about. So if you have an aldehyde, it favors the formation of the product. But if you have a ketone, like all of you explained, because of steric reasons and electronic reasons, the aldehyde is preferred. Okay, so it's not favored. That doesn't mean it's not going to make products. We don't care on paper, right? But when you go in a lab, you're going to have less of the acetyl coming from the ketone. All right, that's all they're saying there. Got it. Now this is, you're making what is called as a cyclic acetyl. Okay, cyclic acetyl. And this is useful for like, it can be used as a blocking group. That's why this reaction is used. Okay. Adele, can you turn off your?
Oh, yeah.
So this is used as a blocking mechanism for the carbonyl group. Okay, blocking mechanism. So it's the same thing, the steps are all the same. 3 steps. This guy is going to tag along. Okay, he's like his Siamese twin. So he's going to be like, behind him. And then these two will combine to give you the cyclic acetyl. So the mechanism is the same, but ultimately you get a cyclic structure there. Okay, so it's called a cyclic acetyl. And this alcohol, what is that alcohol? Has 2 OH groups in the same structure, so that's a diol. Okay, that's 1,2-ethane diol. That actually is ethylene glycol, which is antifreeze. Okay, this particular example. All right, so you can do that. Well, you don't want this chain to be too big, okay, but it still works. Got that? So we'll be using this to block off. Remember, we had a blocking mechanism for the Grignard reagent reaction. We have a blocking for the aromatic substitution with the sulfuric acid. Okay, and this is the third blocking mechanism. Okay, so what is this all about? Okay. So this here we are talking about how it acts as a protecting group. Okay, same as blocking when needed. So I'm going to give you the reagents. Can you draw the structure? And remember, you need an acid catalyst. Can you draw the product? We just talked about it. Can you put this guy on top there? Remember, you need 2 single bonds from here. See that? And we would put an R group there and an R group there, but this R group, they are connected to both. That's it. Okay. Cyclic acetyl of, what's the name of this compound? Okay. Cyclic acetyl of, you can just simply say a ketone. Okay. Now you've blocked it. How do you remove it when the reaction is all done? It's very simple. We have not looked at the mechanism, but you simply use water to get the diol out. And then H3 of this. Okay. So when you take the diol and this, ultimately what is happening is a molecule of water is removed. Okay, it's like a dehydration reaction. And then on the reverse side, you have to give that water back. Okay, so they're saying water is added. Okay, to look at it conceptually. All right. So anytime you want to block that because that's reactive in a synthesis problem, you're like, cap it off. Okay, and then when you do something else with the rest of the molecule, go back and remove the block. Okay. Consider how this synthesis can be accomplished. What is happening here? Look at it. What are the changes that are happening? You have 2 carbonyl groups, right? Are both the carbonyl groups getting affected? No. This is retained. What is happening here? Can you look at just this change? What's the functional group there? What's this functional group? It's an ester. What is this functional group? It's a ketone. So the ester is reacting. What reaction is this? What do you call that reaction?
Reduction.
Reduction. Very good. Now, do you remember what you need for ester reduction? What are the reagents normally used for reduction?
LAH or
Okay.
there's the other one. It was like NBH4.
NABH4.
Very
Yeah.
good. NABH4. Very good. Now, if you have an ester, can you use both? If you have an ester, can you use either one?
No.
Do you need a more powerful one or a milder one? Of these two, which is more powerful?
LAH.
LAH. So for esters, what do you need? Convert an ester to a primary alcohol. We need a more powerful reducing agent, and so we need LAH. But while we do this, now LAH can reduce all of them. Can reduce aldehydes, ketones, esters. Okay. Acids. But NABH4 can reduce only the aldehydes and ketones. Okay. Only aldehydes and ketones. You have to remember some of these things you have to remember. You have to review regularly for the next 3-4 weeks. So if I use LAH here at the beginning, it would kill this. It'll just make it into a cyclohexane, and you'll get that alcohol. Okay, so if I just did this, then I would have this product. I'm sorry, that's a ketone, so it becomes a secondary alcohol. I spoke too soon there. Okay, it's a secondary alcohol here. And then on this side, it becomes a primary alcohol. And then you'll have an ROH molecule. Okay, so this is what you would get. But if you look here, they do not want this to change into an alcohol. They want this retained. So now what do we have to do is we have to block that guy. Okay, we have to block it here and then react with LAH. I think that we have some structures on the next slide.
Can we use like TSL, ET3N or something?
Say that again.
Can we use that TSCL, ET3N?
That is to block the OH. If you have an extra OH in a Grignard reaction, that's what you use. So you cannot interchange because that's for blocking an alcohol. This is for blocking a ketone. So first step, you already know this. I'm going to go over it quickly. Okay, here you lose a water molecule while you block this carbonyl. Remember, this reaction is only for ketones and aldehydes. It does not react with the ester. Not so many restrictions. So you have the cyclic acetyl. Now, while that is blocked, down on his head. Okay, and you'll have another ROH on the side. And then what do you do? What do you do to remove the crown? You add water. So you should be able to show the steps, how you block it. Any reaction, here you're doing a reduction reaction, and then you unblock it. Okay. Remember, halfway through the mechanism, we got what is called as a hemiacetal. And the next slide. This is glucose. Okay. So you'll be learning about this in biochemistry. Carbohydrate chemistry, especially. So this is a glucose open chain, but it is an open chain for a very, very short period of time, or this is more favored, okay, depending on what it is. The cyclic hemiacetal is favored. So your glucose structures, when you learn about this, they'll always be in this cyclic hemiacetal form. And because of this, you know, this OH is a reactive OH group. And you learn more about it, you know, like I said, in biochemistry. So this is a very important application of what you're learning here. And then you will also see that this hemiacetal can be converted into an acetyl group. This is just a single molecule, right? Monomer. But when you have starch or oligosaccharides, which means there are small number of these carbohydrate molecules in the chain, the linkage happens through here. So when you have starch, the 3D structure, the linkage is through this. So you'll have like that, and O connected to another structure like that. Okay, so those are acetals. I wish I had a better picture of the starch structure. Maybe next time I'll pull one up for you. So what is your hemiacetal? Is you have one OR and the other is an OH. Most often these are difficult to isolate, not isolated, because we are forcing the reaction to happen. But then if you react this with another molecule, okay, then you have the acetyl plus water, right? Now remember Le Chatelier's principle? This is an equilibrium. When you keep removing the product as it's formed, it'll shift to the right. Product removed as it forms to shift equilibrium to the right. Okay, those are tricks of the trade. They're saying cyclic hemiacetals, though, like we saw the glucose, you know, those form and they are more stable. Okay. So acyclic hemiacetals are difficult to isolate. Acyclic. but cyclic. Okay, again, a lot of theory. We're not going into the details of it. All right, but just remember that this is an equilibrium, and so any of the factors that influence the equilibrium to form products, all those apply here based on Le Chatelier's principle. How do you draw a cyclic hemiacetal? Okay, so this is going to that's your ROH. Okay, this part of the ring is your ROH. You don't have to spend too much time worrying about how this is made. Okay, what is happening here? Let's number the carbons. 1, 2, 3, 4, 5, 6. Okay, you don't have to draw it on an exam, but this is what happens. You would have to show it. I asked them to show it when we do biochem, or when they took biochem lab with me, to go this way. 3, 4, 5, 6. So this is this OH, this oxygen. And this is this guy. Got that? So here, this is an internal reaction. Here's your ketone on this side, and this side is your ROH. Okay. An internal reaction. And then, yes, I remember we would make structures of these and then like pull it in to see how these are formed. So, all right. So as long as you know the mechanism for it and know how they are used as groups for protecting the carbonyl of an aldehyde or a ketone in reactions, that should be sufficient for you, okay? The next 15 minutes or so, I'm going to talk about nitrogen nucleophiles. They are very similar to the oxygen nucleophiles, okay? And I'm going to be very objective, only cover what we need. And, the carbohydrate part I thought was relevant since you're not going to be studying about that next semester. Now, under acidic conditions, aldehydes and ketones, they react with primary amines. Okay? So we have to know the difference between a primary amine and a secondary amine. Now, a primary amine or any amine has 3 bonds, okay, unlike carbon. So when the nitrogen is attached to 1 carbon, that's a primary amine. When the nitrogen is attached to 2 carbons, that's a secondary amine. And of course, 3, and that's possible too. When you get to your unknown, some of you may have amines. Okay, tertiary amine. Got that? So you need to know how to classify carbon compounds, as primary, secondary, and tertiary, and also know how to classify nitrogen compounds as primary, secondary, and tertiary. And then you'll have one more. Let me make these R groups. You can have another R group. And what happens? Nitrogen loses its lone pair. And what do you think this is called? Quaternary. Okay, amine. So those are the 4 types of amines. Okay, got it? Now we're going to look at the reaction of a carbonyl with a primary and a secondary. So those are our variations. So now what happens here? Okay, that's your benzene ring. This is your primary amine. Right? In the wrong spot. Just call it a hydrogen. What happens here? Now here the reaction is only with one molecule. You need to remember that. This is an imine. And you have a carbon nitrogen double bond instead of a carbon oxygen double bond. Okay. Again, acidic conditions. So you know what the first step is. And even in the formation of the imine, you will have an intermediate structure. Just like with the acetyl, you have the hemiacetyl. Here the names are a little, you know, I wish they had similar names. Okay, so the intermediate structure is called a carbonyl amine. And the final structure is called an amine. Okay, so acetyl, hemiacetyl, carbonyl amine to an imine. Now I'm spending time with nitrogen nucleophiles because after I wrap up this chapter, I want to do a few sections from carboxylic acids and amines. Okay. And the reason being, when you go into biochem and start learning about amino acids, so you need to know at least the physical characteristics and some reactions of carboxylic acids and some for the amines. Okay, so that's my intention. So we are learning about amines here from primary amines. So it's good to know how these amines react, so you'll understand better how amino acids in general will react. So again, a long mechanism, but the steps are very similar. Okay. Now, I'm going to switch this around. Okay. They do this because, see, we were taught under acidic conditions, the acid attack will happen first and then this, but this is quite reactive. Okay, so that's why they show that here. So I'm going to go by what we had talked about before. I'm going to have the acid attack first. Got that? So that we are clear about our we're consistent with what was taught to you before. And I'm sure it does go that way, okay? Because it's more reactive, but we'll just follow our rules so it's less confusing for you. Okay, so we have proton transfer. Okay, remember a water molecule is formed as well. I'm not showing that because of space issue. And then I'm going to show my primary amine coming in. Make that an R group. And at the end of the mechanism, you can change it to whatever I ask in the problem, okay? Nucleophilic attack. Okay. Now, can you perform the next one too? What should we do to clean up the structure? Deprotonation, right? So far the steps are the same for the ROH reaction and this, right? So I'm keeping it consistent. Now we have to remove this tail. I'm just going to say proton transfer, and I think you understand by now what that is. And I'm going to show the structure, so it'll be easier for you to follow along. Okay. So this is halfway. 1, 2, 3. Okay, 3 steps. We are halfway. And what do we call this guy? Let's start learning names. Carbinol amine. Okay. And then we have to go to the next step. What do you think is the next step? Now let me draw the final structure. This is your imine. Why is it an imine? Okay? Imine, but because of the double bond. Okay? Like an ine sound. That's your final product. So what do you think you should do to the carbinolamine? Ideas? Let's make it interesting to learn.
Would it be the loss of a leaving group?
Yes. Loss of the leaving group. Now, is OH a good leaving group?
No.
No. What must you do to that guy?
Protonated.
Protonate. Okay. So the steps are very similar. So he's ready to go. How is the reaction initiated? Something that this lone pair does. Okay. You're almost there. The steps are, I would say, exactly the same as with the acetyl formation. Now the nitrogen has a positive charge. what will he do? Proton transfer and use another molecule of water. Okay, I'm not drawing everything out because it's, you can see it better that way. Okay. Carbonyl amine and imine. Okay, 109, a couple more slides. Okay, very, very similar. You need to write out each of the mechanisms without looking at anything, okay, to practice. A couple more slides, more qualitative. So we are doing the reaction under acidic conditions. So this is what happens. Protonation of the carbonyl is not the first step of the imine formation, okay? And these are the details for it. I'm going to say just follow the steps that I had given, and we will not worry about it here, okay? So just assume, or no, I should say no, protonation is not usually the first step, but you can follow the same mechanism that I gave you. In the last slide. Okay. And the reason why they're saying that is that your amine itself gets protonated with the HCl or any acid that you have. So your amine is not like that, waiting to be a nucleophile. Your amine is more like this. Okay, so your primary amine becomes an acid, okay, is more of a protonated amine. So this itself can react as your acid, okay? So don't worry about all the technical details. So just remember, when you have an amine, contrary to what was said, protonation may not be the first step, but for our learning here, we're just going to assume that protonation with H3O plus is the first step, and then do the nucleophilic attack. All right. Another technical detail, the reaction cannot be too acidic or too basic. It has to be under 5. Remember, enzymatic reactions also require an optimal pH. When you have a lower pH, like we said, all your primary amines are protonated. Okay. Because you need a free nucleophile. No free nucleophiles. You want them free like this. You want your nucleophiles to be available for nucleophilic attack. So if you have too much acid, they become protonated. And if you raise the pH, then all the acid used as catalysts are neutralized. Okay, you need an acid to initiate the reaction. So there is a fine balance, like with enzymatic reactions, and that's what it is. Got it? Okay. Now, when you come to class on Monday, I want you to write the mechanism for this reaction. Okay, this is the reaction with the secondary amine. And you can upload it on the chat when we come up. We'll see. You can take a picture and show it to everybody. So here again, with the secondary amine, you will get in between a carbonyl amine. And then this is not an imine, because look at the structure. There's no carbon nitrogen double bond. It shifts over because the nitrogen still has to have 2 single bonds. So this moves over, and this is called an ene. Like enol, remember? Enol. Double bond and an alcohol, double bond and an amine. Wow, light bulb, right? So, but the steps are all the same or very similar. Okay. Now, so remember to do that for Monday. And I posted a homework last night, and that'll be the last one for chapter 18. And I think it's due on Tuesday, right? And let me stop sharing. And I'm still recording, which is good. And you may want to look at the end of the last recording, Wednesday's recording. I would have whatever I missed. Okay. Are we still there?
Yeah.
Mm-hmm.
Not able to see my own video, but that's, oh, there I am.
There's no lab binder due today, right? It's just the theory, and I think the post lab.
Let's go over that. Anything due today for lab?
I know the theories do.
Theory is due for the alkylation lab.
Yeah,
Okay.
7.4.
Binder, okay. Anything else?
Dr.
UV, post lab, right?
Yeah, so it's just the UV post lab and the theory, I think. No
Yeah.
lab binder, right?
Pre-lab is due today too.
Mine says pre-lab and binders due as well.
Oh, okay.
Mine says binder.
Yeah.
Okay.
So you have to
And
do it like how you would do for a regular lab. So you have to do
Okay.
everything that you would turn in for a regular lab. And then for last week, you'll do the UV post lab.
So
Look
lab
on-
binders are gonna like be due on Fridays now, right?
Well, for this week, yes.
Okay.
Next week, the unknown will be due Friday. And then you'll have one more binder to do. That'll be all. Next Friday or next Saturday, or, because it's Good Friday. Or maybe Thursday, because it's just an unknown. You don't have to do any write-up. But look on Canvas. Look at the announcement, because I may not remember everything. And you have to submit accordingly. And here's what I have for next week. Monday, 12 to 1:30. And Tuesday, I'm finishing another class at 12:30. So 12:30 to 1:30, we'll review carbon 13 and any questions you may have from UV. And then I'll finish off that section from carbon 13 at the end. And then Wednesday, 12 to 1:30, 12 to 12:30, you're taking the quiz. And do you know what sections you have to review for the quiz? 18.7 through 18 point, till the end. Till the end. And you don't have to know the mechanism for elimination addition, but you have to know how to predict products. 12:40 to 1:30 lecture. I upped that a little bit because we are making announcements and things like that. But if you have something pressing at 1 on Monday or Wednesday, let me know. And then Friday, no class. That's Good Friday. And that's another reason to make up for some of the lost time in the past few weeks. That's another reason why I'm doing that. And next week, which is by April 10th, I think I'm going to make that April 9th so y'all can ask questions, because yours will be an individual one. And like I said, it takes about 2 hours if you sit down and work on it, or less. And then we'll have to fix a date for quiz 3 for lab.
Dr. Mary,
Uh-huh.
Shelby wanted to know if for the lab that we have due tonight, if we're doing the procedure for both the kinetic control and the thermodynamic control, or just one or the other.
When you are in lab, what we've done is we make you write the whole thing, and then you'll work in groups of 2. And let's say you do the kinetic control, the person next to you will do the thermodynamic control. So you needed procedure for both. And the procedure is almost the same. John asked this question. So what you can do is you can copy whatever you've written for the kinetic part and then paste it for the thermodynamic and make the changes.
Okay.
Okay. So if you copy from your own, that's okay. Does that make sense?
Yeah.
Okay. Any other questions? I can't think of any other, but I'll be posting sapling for 19. So the next 3 weeks, all the teachers are going to be bombarding you because, everybody's sort of up to speed and we are following a routine. So try to keep up. And I'm trying to space our assignments and assessments so you're not overwhelmed. But what I ask from you, especially for the lecture part, to keep up with the reading. Do not give up on that, okay? Just review a little bit every day, do practice problems every day. Try to do practice problems without looking at anything. Go back and start reviewing, stuff from like 18 or some of the reactions that I reminded you of the other day that you need to know from chapter, like the alkene chapter or the alkyne chapter. So go back and look at those. Okay. Anything else? Okay. All right. If you have nothing else, then I'll stop the recording first of all. And then if you have any questions, just email me